Okay, let's get back to our cliff here, guys. Going off the cliff. So basically what we're doing with this is we're coming up with a physics model in order to be able to tell things like forces and moments, velocities, angle at which it hits the ground. Waylon, why would an engineer want to know these things? Or, yeah, it's great to figure out conditions at the bottom of a car crash, but why would an engineer be assigned a problem or come up with a problem to analyze something like this for a car?
To like figure out the things that could prevent like car crashes.
Yeah, absolutely. So in order to know what speed it's heading at the bottom of the drop, I'll show you guys how to do this. There's an angle involved here too, so you can figure out at which angle it hits, because I think from just an intuitive perspective, the more vertical it hits the ground, the probably worse it's going to be. The more it lands on its wheels, the better it's going to be. So it's going to totally have an impact on crash testing. Darren, have you safety administration? Me either. Not until I started working at Goodyear. That is the federal agency that sets like rules for the highway. So, amongst other things, they have crash test ratings, crash test dummies, that kind of stuff. There's actually a scenario where they release like reports and say, okay, American car makers, you're going to have to, among other things, make sure the car survives a fall off a cliff of 200 feet going 30 miles per hour. It'll look like that. So when I was at Goodyear, there are hundreds of these for a car and dozens of these for a tire. So say, for example, every tire was tested to be blown up. So literally they would stick it on the air compressor and put a bunch of air in it until it blew up. And they did that for aircraft tires. Charlie, why do you think they would do that for aircraft tires? Because they blow up pretty often. You think about it. Who's ever been on an airplane here? Okay, but what happened, or how does it feel when you guys land, when the wheels touch down?
Like jittery, like it's shaking a lot.
Yeah.
Like, might pop the tires if it's like going, shaking out. How much?
For sure. Different from a car, right? Like, so the scenario we're talking about is a plane flying, say it's a 737, it's flying at about, when it's landing at about 300-400 miles an hour. And that tire is sitting there not rotating, right? And then it hits the ground. You've heard it from the movies. When the tire hits the ground, when the plane lands, it squeaks and it smokes, and then, sometimes it blows up. And that's the point, is that type of loading, to go from not spinning, not hot, it's cold, it's up in the it's up in the landing gears, up in the plane, and it's 40,000 feet up there where it's real cold. So basically, it is an impact. Basically, you just drop. It's akin to dropping the tire from 30,000 feet. This is basically the same thing as the tire landing. So, Ethan Appleton, what happens to a hot, overinflated tire? Pops. So it makes sense that the FAA makes you blow up your tires to figure out at which pressure and which temperature they actually blow up, because it could happen that, when it does happen, that the plane is going to blow up some tires when it lands. Ethan, what's the engineering solution to blown up tires? That's one, yeah, that's not the one I was thinking of though. That's close. More tires. More tires. That's the one I was looking for anyway. The ones you had were right. That's called redundancy, right? One tire blows up, and there's, on a 737, I think there's 16 tires, so there's 15 other tires. A semi-truck, so moving over a little bit more. You guys have all seen those going down the highway. They even have a name for it. It's called an 18-wheeler. That's the nickname for it because it literally has 18 wheels. And on the trailer and on the rear two axles, it has two sets of tandem tires. So those things go out all the time, but it's never a big deal because when one goes out, there's 17 other tires to pick up the slack, and that's how it's designed. So. Okay, Ethan, following on to that, why would it be good to know this angle?
To see if it actually line up with tires or not.
Yeah. Yeah. All right. So we're talking about vectors, we're talking about free body diagrams, we're talking about, hey, how's it going, man? We're talking about physics, we're talking about analysis, engineering analysis. So what I'm trying to do now basically is connect you guys over to the why. You know, this is all fine and dandy to do this type of analysis, but why would you do it? You would do it to, if you were, say, an engineer at General Motors or Toyota, and you're designing a new tire, literally every new car would have to go through the same analysis. So that's the end result of it, is so you know how to do that, basically, to figure out how fast the car is moving here, and in what direction. What else might you want to check out? I don't know, I'll think of something. All right. F equals ma. It's an equation. It's also one of Newton's laws. I believe it's the third one. Charlie, could you tell me what that means? Come on in, Brian. Sorry, go ahead.
Force equals mass times acceleration.
Okay. Can you tell me, we talked about this yesterday a bit. Thanks, Brian. And what is acceleration?
Changing the speed over time.
Yep, that's exactly what it is. Change in velocity, actually. That's picking hairs, though. Charlie, what's the difference between speed and velocity?
Direction.
Thank you. Exactly. Okay, so this A right here, Charlie, what happens to the force if there's no acceleration?
It's zero.
Right. So what that means is, that's got a couple of physics meanings, is that if there's no acceleration, there's no force. So the car traveling at 30 miles per hour going off the cliff, and then after it goes off the cliff, if it's got no force in the other direction, it's going to keep going 30. So that's what that means, is that for every force, there's a change in velocity. That's what a force does. That's the definition of a force, basically, is that when acted on over enough time onto an object, it will change its velocity or its temperature, but that's a different subject. Michael, what's the M here? Mass. I know it's kind of hard to describe, but what is mass? What is matter?
Like the space it takes, not necessarily the weight. Like how much space takes in a given space.
Yes. Density, so here's another value, is mass over volume. And what that means basically is that, let's see here. I gotta see a piece of steel laying around. it's more dense, this metal object or this paper form? Metal. You can kind of intuitively feel that too. If you were to take a 1-inch ball and make it out of rubber, make it out of steel, make it out of paper, which one would be the heaviest? The steel one. Now you can kind of intuitively feel that. You know, if you had a 1-inch steel ball, which one would be heaviest in your hand? Probably the steel one. That's because, given the same volume, steel packs in more mass. So, oh, here's a good one. Darren, can you tell me something that has infinite density? That's pretty close. Black hole. A black hole, basically, the top number goes up to infinity and the bottom number goes down to nothing. So that's what a gravitational singularity is. It's basically the sun collapsed down to a single point. And as you guys know, that's pretty small to pack that much matter into, which is why a black hole is a black hole. But we're not talking about black holes today. All right. Waylon, what's Vx at time equals 1?
Could you repeat that?
What is the velocity in the x direction at time equals 1?
It's the velocity going like forward. Or,
Side to side.
yes, that's it.
What is the number?
30 miles per hour.
Yep. Charlie, what's the horizontal velocity at time equals 2? Yep. Say this is the ground. I'll say if you guys suspect it's 30 right before it hits the ground. So it's traveled all the way down to the ground, and it's the instant right before it actually contacts. It's still going 30 miles per hour. Okay, that's our free body diagram. This is the actual physics model. We talked a bit about this yesterday because we're considering it to be 0. So we're assuming it to be 0. And because that wind equals 0, this is 0. What does that mean over here, Jaden? If there's no force, there's no, which is a, you're right. There's no force, there's no acceleration, and acceleration is a change in what?
Velocity.
Right. So that means if there's no force, there's no change in velocity. So there's another one of Newton's laws that says something like if an object's traveling, it tends to travel, or it tends to, wait, how's that go? An object in motion tends to stay in motion, and an object at rest tends to stay at rest. So what that really means is, and that's Newton's first law, I believe, that what that really means is that when an object's moving, unless a force comes along and does something about it, it's going to keep moving in that exact same direction. So if you accelerate something to 30 miles per hour and you don't put another force in the opposite direction, it's going to keep going forever at 30 miles per hour because there's no change in velocity. All right. Darren, what's the velocity in the vertical direction when it's still on the cliff? 0. Ethan Lamar, what is the velocity here at time equals 0? Time equals, excuse me. What's the velocity at time equals 1? Time equals 0, I'm sorry. Time equals 0, it's actually gone off the cliff a little bit. It is governed by this equation. So this is kind of a trick question, Ethan, I'm sorry. Wait, is that right? Let me look up this equation here, guys. Having a brain fart right now. Okay. We'll get into this equation here in a second. But the velocity at any given point, and we don't have, it's okay if you don't know this equation because you haven't seen it before. What this is saying is that the velocity in the y direction, because it's being accelerated by gravity, is a parabola, right? So for every foot that it travels down, it accelerates 4 times. So that means with this equation, we can go ahead and figure out what the velocity is at each point in the y direction just by knowing the height at what it is and the mass that it is. So that equation is one thing that Sir Isaac Newton discovered with his apple. So Waylon, is gravity constant?
Yes.
So what does that mean? Gravitational constant means that no matter what happens or where you go, if you have the same mass, it's always going to pull on you by the same amount. Same thing with this car. So I know this is getting a little busy here, but as it goes off the cliff, basically, and then another color. Let's just draw it like this. It's the same gravity acting on it here, 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 and here, and here. It's always acting, right? So that means if there is an acceleration, which gravity is, there's a force, which gravity also is. So gravity's, or that's the number that shows up on the scale. All right. Let me go ahead and erase that. Anybody have any questions about this? No? Darren, what's the maximum velocity that a skydiver can attain? Yeah, you guys have probably seen the skydivers on TV or movies or whatever. They keep falling and falling and falling, and there's a force acting on them. Should they keep accelerating as they're falling towards the earth? I mean, what's to stop them from going 1,000 miles per hour? What's the force acting in the opposite direction? Yeah, exactly. If there was no wind and somebody jumped out of an airplane, they would get to 1,000 miles per hour. So what that means is that when somebody jumps out of an airplane, gravity's acting on them, right? All the way down to the ground. There's a force acting on a person to accelerate them, to change its velocity all the way to the ground. But you guys can kind of intuitively feel that that's not true. A person isn't going 3 times the speed of sound when they hit the ground, or if their chute doesn't open. So what happens? There's a force in the other direction. There's actually something called a terminal velocity. You might have heard that term before. What a terminal velocity is, it's when the wind resistance force exactly equals gravity. And that means that you continue falling, but you don't go any faster. So when you're spread out like this and you're falling towards the earth, the wind is pushing back against you enough to counteract gravity. Ethan Appleton. In the space station, the International Space Station, this is more of a thought experiment. Do the astronauts experience gravity? They do? Aren't they floating around the station and, you know, just kind of floating through doors and stuff? Yeah. So that means they're not experiencing gravity like we do. So when they get out of their bed and they try to stand on the ground, they float up. That's what happens when gravity goes to 0. So why would that happen? Charlie, the space station's doing what around the Earth? Okay, so what is an orbit in the shape of?
Circle. Okay.
Something goes around in a circle. Does it ever get closer to the center?
No.
All right. Because it's not moving radially, it's called. There's no acceleration. There's no gravitational acceleration because there's no change in velocity. That means there's no force, and in this case, that means gravity. So because you're not moving relative to the Earth when you're in space, you're just moving around it. That's why you don't feel gravity. What's the opposite of this? Ethan, if I took a bucket of water, swung it around like this, what would happen?
You get less speed of water, so you stay in the bucket.
Exactly. So Ethan just stumbled upon the design of a spaceship that's going to take us to another planet. Basically, it's going to be a big long cylinder that spins to induce artificial gravity, basically. So let's say our pail of water let's skip the pail of water for now. Okay, okay, we're gonna go into a different part of the lesson here. Sorry guys, my writing's kind of chicken scratch, but Brian, can you read those two numbers?
50 and 30.
Yep. And what are the two variables? This is Vx and that's Vy. So velocity that's going in the x direction, the velocity is going in the y direction. 30 and then 50. So those are just two numbers I'm giving you. Waylon, how can we figure out how fast it's actually going? By combining those two vectors, they're called. So basically I have 30 miles per hour in this direction and 50 in this direction. So what I'm getting into here is a little bit of vector math. So where do you think the resultant direction is going to be when you add those two together? Like this, and like this.
Is it going to be 80?
Not quite. Good guess though. Adding things together in a scalar manner is how we did things with speed, but these are vectors, so direction matters. So that's actually what I'm trying to get to. If you push something, so if I push something in this direction, like this, which way is it going to go? It's either going to go down and to the right. So if this thing is going 30 miles per hour in this direction and 50 in this direction, when you add those two vectors together, it's going to be somewhere in here. So that means that when this car hits the ground, its velocity looks something like that. Darren, how might we figure out what that resultant is? We mentioned it yesterday. There's an equation. Close. Ethan, can you tell me what this actually, what shape this resembles? These three arrows? Thank you. That's a right triangle. So I mentioned yesterday sines and cosines. Weird. That's where this comes into play. So we're going to start talking about vectors now, it's called, and vector math. So if something is going 50 miles per hour in the vertical direction and 30 miles per hour in the horizontal direction, how fast is it going? So yesterday we had an equation. Mr. Pythagoras. Pythagoras was a Greek dude from the BCs, 300 BC or something like that. And back then they had guys just sitting around, well, I guess like they do now. All Pythagoras did was draw triangles and figure out stuff about them. So he figured out that if you take 50 squared plus 30 squared and whatever this is, and square it, add these two together, they're equal. So, who's taking algebra? All right. That's our equation. Charlie, can you tell me from, this is hard to figure out by hand, but how would you go about solving for C?
I think I would just take the square root of 50 squared plus 30 squared.
Not quite, your PEMDAS is a little off. You have to add them together first. So it's against PEMDAS to square root and then square root because of the plus sign. So what you have to do is calculate 50 squared plus 30 squared and then take the square root. So can anybody math out their 50 squared plus 30 squared for me?
50 squared, 30 squared is 3,400.
Got it.
It's a root to whole number.
Okay, so then take the square root of that. Okay. Does that sound reasonable? So if I'm going 30 in this direction and 50 in this direction, this is saying I'm going 58, and we'll figure out the direction here in a second. 30, 50, 58. Does that make sense? Yeah, it does. It does. If it were 508, would that make sense? So you combine a 30 mile per hour and a 50 mile per hour and you get 300 miles per hour. That doesn't make sense, right? So that basically what I just did there is called a reality check or a gut check. I like to do this in my engineering analysis a lot. You just stop every now and again and you go, hey man, does that jive with reality? That answer right there I think does. 58 miles an hour sounds pretty good. The National Highway Transportation Safety Board will likely have a number that there's a cutoff here this has got to exceed. So that's what this would look like. You'd eventually write all this up and put it into a nice big long typed up report and submit it to the federal agency. So that's what would happen with this data basically. Okay. Last but not least, Jaden, what is velocity? Right. So velocity, we're always going to want to find out speed and direction. So we just did speed. And we need to find out direction is the angle at which it hits the ground. So does anybody remember sines and cosines? All right, it's okay if you don't. Basically, this is kind of a self-contained mini vector geometry lesson, so we can kind of move along with our engineering stuff, because unfortunately, you guys have, usually in engineering school, you take physics first and then engineering, so, but that's not available here. So we're doing this as a self-contained trigonometry lesson, basically. So in order to find the angle of this velocity hitting the ground, You got to pull out one of the three sine, cosine, tangent. Okay, when I was your guys' age and I was learning my sines and cosines, somebody told me this kind of little dumb mnemonic it's called, and it's stuck in my head ever since. It's a nonsensical phrase, so, ka, toa, but it governs which sides of which triangles you should take for each of the trigonometric ratios, it's called. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So what that means is, for this angle, this is the adjacent side, which is, adjacent means next to. Opposite means this side here. And for a right triangle, the hypotenuse is always the long side. So, all right, that's enough for today. We'll get into pickup right here tomorrow, and we'll start talking about trigonometry and how to figure out that angle. So, thank you all for your attention today. I really appreciate it, guys. And Ethan, I'll mark that extra credit down. I haven't figured out how I'm going to do that yet, but I will. Thanks for the suggestion. If you guys need to use the restroom, go for it.